The last topic we're going to talk about in this section is the topic of polarity. And polarity is a really interesting result of knowing how the electrons are distributed in atoms, and the effects can be quite drastic. And I'd like to show you two examples of how important polarity is. The first one is to compare water, which is H2O. There on the left side, we saw its bent structure earlier, and methane, CH4, which is basically the main ingredient of natural gas. Now, water is about 18 grams per mole, and methane, CH4, is about 16 grams per mole. And we're going to see in a future lecture that boiling points are basically the factor of a couple things, but one of them is the molar mass. More molar mass, harder to boil. But water and methane are about the same molar mass. But there must be something else going on, because water boils at 100 degrees Celsius, which is where we kind of expect it because we do a lot with water. Methane, on the other hand, boils at negative 161 degrees Celsius. So about 260 or so degrees difference in the boiling points. And again, this isn't from mass because the masses are about the same, all right? So why do water and methane differ so much? The other thing is that why does water dissolve ionic compounds so well? We saw in electrolytes how water can dissolve strong electrolytes into cations and anions, kind of surrounds them and stuff like that. Well, the answer to both of these questions comes from a discussion of the polarity of the molecules, and that's the next thing we're going to talk about. Some molecules have even distribution of electrons around them. Some have, though, an excess of electrons on one side or the other, causing these effects to happen.
When the balloon is rubbed with wool, the wool imparts a static electric charge to the balloon. When we place the balloon near the water, the stream is attracted to the balloon. The polar water molecules act as though they have an electric charge as well. Water molecules carry no overall electric charge, but they do exhibit polarity. The positively charged end of the water molecules and the negatively charged balloon attract each other.
If you remember the structure, the Lewis structure for water, it was basically H, and then there was the bent HOH, and it was bent because on the oxygen there were two lone pairs. Now, water doesn't have a positive or a negative charge, like a sodium plus or a Cl minus, something like that. But these two lone pair electrons give it kind of like a quasi-electric charge, and that's a slightly negative side. But because the molecule is overall neutral, that means the opposite side, i.e. the side with the hydrogens, you have a slightly positive side. So on the animation on the right, that balloon had a slight negative charge, and you can see how the hydrogens there are aligning themselves towards the negative balloon. Positives and negatives attract. On the other hand, the oxygens, which are somewhat negative, are trying to get away from the negative charge. This is a result of polarity. It's unequal distribution of electrons in molecules. A better, sometimes I think, analogy is if you're making a peanut butter and jelly sandwich and you only put the peanut butter on like half the sandwich, right? You haven't spread that peanut butter all the way through. If you don't spread the peanut butter all the way through, you have a polar peanut butter and jelly sandwich. If you spread it all the way through, then it's a non-polar thing. By the way, you can do this experiment, but you have to use a very thin stream of water. Don't like have the faucet go full blast and expect for it to do it. But if you have a very narrow stream of water, you can make the balloon actually pull it over. It's kind of cool. Polarity, then, is just an unequal distribution of electrons. So, for example, in H and Cl has 3 lone pairs and hydrogen doesn't have any. So chlorine has a lot more electron density around it. We would call it polar because there's a positive end and a negative end, and each of those is like a pole, a positive pole or a negative pole, and because there's 2 of them, it's a dipole. So HCl is polar with a positive and a negative. And notice the notation here. If the slightly positive side gets a delta plus, so hydrogen is somewhat positive, the slightly negative side gets a delta minus. That little symbol there is a lowercase delta. So the chloride with more electron density is delta negative, and the hydrogen here would be delta positive. This arrow system is also used. The positive, the left-hand side of, if you will, the arrow is like a little positive symbol. That's the positive dipole, and the arrow points towards the negative dipole. And you can do this for all of them. Polarity you can do a lot with vectors with. If you get to higher courses, vectors are used in math sometimes to represent direction. And vectors come in really handy when it comes to polarity in higher chemistry courses. But for right now, we'll just kind of talk about it in a vague sense. Chlorine has a slight negative charge, or a delta minus, and the hydrogen has a slight positive charge, which would be delta plus. And again, sometimes you'll see that arrow system all means the same thing. You can actually measure the polarity, and you measure the polarity through something called a dipole moment. And dipole moment gets the symbol mu. If you have a non-polar molecule and you place it in an electric field, the molecules don't align themselves. That's because in the case the green molecules on the right, the dipole moment would be 0. There's no interaction, no difference in polarity. On the other hand, if you have a polar molecule, then the negative side of the molecule will align towards the positive, and the positive side of the molecule will align towards the negative. So I know from the diagram on the left that the white triangle represents the negative dipole, and the blue triangle represents the positive, because positive is pointing towards the negative side of the field, and the negative right there would be pointing towards the positive. So polar molecules have measurable dipole moments, and there's machines that can do this and stuff, which is pretty cool. Non-polar molecules could care less. They just float around like nothing was happening. Now, an interesting thing happens. Because of polarity, the Hcl bond strength is quite a bit larger than we'd expect for a regular HCl. So a regular bond, a regular HCl, they feel would be about 339 kilojoules. But in the real world, when they measured it, it was more like 432 kilojoules per mole to break HCl. So there's a lot more attraction. And that's because the H and Cl can combine a little bit with another ClH. So you can see the H and the Cl then are opposites, and this Cl and H are opposites. I like to think of polarity as being a kind of a stickiness. The HCl's are sticking more to each other than we think, and that's why the energy is a little bit higher. The difference between what they feel it should be and what actually it is, that difference is related to something called electronegativity. And electronegativity gets this symbol chi. Looks like an X. You can use an X, but it's technically chi. Anyway, electronegativity is really useful. Electronegativity does describe polarity, but it also can be used in Lewis structures. We'll talk about that in a little bit. There's a polarity guide in the companion and online if you'd like some more information on it. This is a table showing the relative values of electronegativity. And what's really important to us is that fluorine in the upper right-hand corner, that's the most electronegative element. The noble gases aren't usually included here because they don't usually make compounds and they're kind of boring, all right? But if you think about it, this is another periodic trend. Electronegativity increases up and to the right. So if you look on the group 1A on the left side, francium to cesium to rubidium to potassium to sodium, they're slowly getting bigger as you go up. And as you go right, they slowly get bigger until you get to fluorine. Fluorine is the most electronegative element of all. And that's why fluorine as an oxidation number in a compound was always -1, because it's the most into electrons. It attracts electrons, if you will, better than anything else. Oxygen is second to fluorine, 3.5. Nitrogen and chlorine about the same. You can always look back on this table, but it's also kind of nice to know that fluorine is the most electronegative, and roughly it increases up and to the right. Electronegativity has been updated to a different version, but we're using the traditional electronegativity values. The new system is still controversial, so let's talk about that at a different date. But in the regular version, which is still very well accepted, fluorine again has the maximum electronegativity. And in a Lewis structure, this is important, the atom with lowest electronegativity is the central atom. So up until this point, we've been saying like, oh, it's usually the first atom listed and stuff like that, the central atom. Well, now we can say definitively that the central atom is the atom of a lowest electronegativity, as long as it's not hydrogen, right? Hydrogen's kind of a freak unto itself because it only has one bond it can make. But anyway, everything else, the central atom is the atom of lowest electronegativity, so it's pretty important. But in addition to that, relative values of electronegativity, i.e. comparing one atom to the other in electronegativity, can determine bond polarity. And bond polarity is one way that chemists use to understand why certain types of molecules will attack a second molecule and why other ones won't. So this is just a question you might come up against. You don't have a table, but it does say which of the following groups is arranged correctly in order of increasing electronegativity. Now again, the goal here is to figure out electronegativity. If it's increasing, it increases up and to the right. So you want the most down and to the left atom, all right, to start with, and you go to the most up and to the right. And we talked about how fluorine is the most electronegative element of all. So if fluorine's one of them, then the answer has to be A or C. It wouldn't be aluminum because aluminum is certainly not up and to the right at all, but fluorine is. So if you look on the periodic table and you go up and to the right, aluminum is under boron. So aluminum would be first, boron would be next, oxygen more to the right of boron, fluorine the most electronegative of all, answer C. This question goes into more about the relative values of electronegativity, and it says which bond is more polar, which one has the biggest difference in the dipoles, i.e. the dipoles being positive and negative. So if you look up the value of electronegativities I showed earlier, oxygen is 3.5, hydrogen is 2.1, and fluorine is 4.0. Now, some interesting things from that. The first of all is that the relative electronegativities is that delta chi, and you can see the OH has a bigger delta electronegativity, 1.4, than OF's 0.5. So one thing we would say is that the OH bond is more polar. It has a bigger separation of electronegativity values. But there's another thing you can pull out. The bigger electronegativity value will be the negative dipole. So on OH, the oxygen is the negative dipole. Hydrogen is the positive, oxygen's the negative. This is what we saw with water. But with OF, it's reversed. Fluorine has a higher electronegativity, so fluorine is the negative dipole. Oxygen is the positive dipole. So there's two things you can glean from these electronegativity values on this problem. First of all, OH is more polar. It's got a bigger positive-negative separation, if you will, than the OF does. OF would be closer to a pure covalent bond, which has really small delta chi. But the other thing that's really cool is that on OH, the oxygen is the negative dipole, but on OF, the oxygen is the positive dipole. Bigger electronegativity, negative dipole, smaller electronegativity, positive dipole. Which of the following pairs of bonded atoms would you expect to have the greater bond polarity? Okay. Now, if you look right away at the bottom, you've got fluorines, and it might be tempting to say, oh yeah, fluorine, most electronegative and stuff. Okay, that's cool, but if you're looking for greatest polarity, you want the biggest difference in electronegativities. And fluorine has an electronegativity value of 4, which is huge, but 4 minus 4, guess what? 0. So E is not polar at all. It's actually nonpolar because delta chi is 0. So how you want to answer this problem is you want to find the two atoms which are furthest apart on the periodic table, and usually that's a great answer. A better answer would be to go through and find all the individual electronegativity values and find the difference between them. But using the first way I mentioned, K and F are pretty far apart on the periodic table, so my money would be on answer B. And sure enough, that's it. N and O are pretty close to each other. That's probably not it. N and B, not too far. S and Cl, not too far. FF, like I said, are right next to each other. Most of the time, the atoms which are furthest apart from each other will be the most polar.